Hey, ladies and gentlemen, Mr. Robeson here. We are working on the arc length formula today, 7.3. So I'm going to break this up into two videos, but they shouldn't be too long. I don't think they're going to be long. So first up is we're going to go over how to derive the formula for arc length. So arc length is the length of a curve between 2 points as traveled along the curve. So like if we're going to get from this point right over here to the point over on the other side of the curve over here. So like if going to there along the curve, we've got to use a different formula than if we were to just go straight between them, where we would just use the distance formula. All right, so the idea here is we break the curve into a bunch of really small sections. Like these sections they have right now are pretty big, like really, really small, like there to there, there to there, there to there, these tiny little steps. And we find that we treat each one of those little things as a line. We use the distance formula of each of those little sections. We sum all of them up, and then when we take a limit as that or as we go to an infinite number of sections and the width of the section goes to 0, that's where we get the integral from. All right, so what happens is, so remember the distance formula, it's the square root of the change in x, x1 squared, plus the change in y's. All right, well, the symbol we use for change is often delta x. So we have delta x squared and delta y squared. All right, and that would be our distance for each little section. All right, so maybe we could put like a sub I here, sub I. So this is the ith interval, the length that it would be. All right, so now what we do to get from this to the actual formula, and we could use this formula, we actually do use this formula when we work with parametric equations. But to get from this to the other formula, what we do is we divide everybody by the delta x squared in here. And then we put a times delta x squared to kind of cancel it out. Outside, still under the square root. So then this first one just becomes 1. Delta y over delta x is essentially dy over dx, and it is squared because they were both squared. And then this little guy, again, we'll treat this as dx instead of delta x, but dx squared, the square root of that. So what we end up getting is the square root of 1 plus the derivative squared dx. All right, and that was just one section. All right, so then what we do is we integrate this over the entire interval. So from a to b of 1 plus the derivative squared dx. All right, and that's our arc length formula. All right, that's it right there. Now, we could have also divided back here by delta y in both of them, and we'd have delta x over delta y, and that would be the derivative of x with respect to y, and it would look almost the same in here, which brings us to our two formulas here. So here's one, and here's the other. So this one is in terms of dx, this one is in terms of dy. So depending on what it's solved for, that's the formula we use. If it's solved for y equals, so if we have y equals some function of x, this is the one we want to use. But if we have x equals some function of y, this is the guy we want to use. All right? Most of the time, it'll be the top one here. All right? But they work the same way. So use the distance formula to find the length of the line y equals 2x plus 1 from 1 to 5. So this is just old school distance formula. So if we plug in 1, we get y equals 2 times 1 plus 1. So that's 2 plus 1 is 3. So we're going from the point 1, 3. And if we plug in 5, we get 2 times 5 plus 1. So 10 plus 1 is 11. So we're going from 1, 3 to 5, 11. And the distance formula would be the square root of x minus x, 5 minus 1 squared, plus the square root of the difference of the y's, 11 minus 3 squared. So we get the square root of 4 squared is 16, and this is 8 squared is 64. So the distance is the square root of, let's see, that's 70, 80. And let's see, 80 is 8 times 10. And that's 2 times 2, or 2 times 2, and this is 2 times 5. So we get two pairs of 2's that can come out as a 4. We get 4 root 5. Now let's try it using the arc length formula and see, do we get the same thing? So the arc length formula says we take the derivative. The derivative of that is just 2. And then we're integrating along the x-axis from 1 to 5 of the square root of 1 plus the derivative squared dx. So we got the integral from 1 to 5 of, let's see, that's 4. 4 plus 1 is 5, so we get the square root of 5 dx. So that's x times the square root of 5 from 1 to 5. We plug in 5, we get 5 root 5, minus plug in 1, we get 1 root 5. And what do you know? Look at that. It matches that exactly. In fact, that might have even been easier. Who knows? We didn't have to find 2 points. All right, so the arc length formula does seem to work for straight lines. It does also work for curved lines. All right, so here's some examples with curved lines. So we've got y equals the natural log of cosine of x. I don't know what that looks like. And honestly, that's probably a pretty ugly graph. But we're going from 0 to pi over 4. We can just use the arc length formula. So we need the derivative. All right, derivative of the natural log of cosine is, let's see, cosine on the bottom. And the derivative of cosine on the top is negative, oops, I was getting ahead of myself here, negative sine. So then we get the arc length is the integral from 0 to pi over 4 of the square root of 1 plus this guy squared. So negative sine of x over cosine of x squared dx. All right, now bells and whistles should always go off in your head when you see sine of x over cosine of x, because sine of x over cosine x is just tangent. So this would be negative tangent of x squared. And the negative is going to cancel out when we square it. So what's going to happen is inside this square root, we're going to have 1 plus tangent squared. All right, still from 0 to pi over 4, still dx. All right, 1 plus tangent squared is one of our Pythagorean identities. All right, that's secant squared. So this just becomes, again, same bounds, square root of secant squared. Square root of secant squared is secant. Technically, it's the absolute value, but secant's positive on that interval anyway, so it's not going to change anything. So it's just going to get secant of x dx. Now we got to think back. Do we remember the integral for secant? It is the natural log, the absolute value of secant of x plus tangent of x plus c, but we're not doing plus c. We're going from 0 to pi over 4. And then we're plugging in both of those. So secant of pi over 4 is root 2. Tangent of pi over 4 is 1. Minus secant of 0, oops, natural log, sorry. Of secant of 0 is 1. Tangent of 0 is 0. Natural log of 1 is 0, so that's all 0. So we just get that this is the natural log. We don't need the absolute value because the square root of 2 plus 1 is already positive. And there's our answer. All right. So it's interesting that the natural log of the cosine curve has a length that doesn't even involve any sort of pi's or anything. It's just natural log of root 2 plus 1. All right, let's try one more here. So another example. Here's our derivative, x cubed over 6 plus 1 over 2x. So we've got an asymptote at 0, and otherwise it's like an x cubed graph. We're going from 1/2 to 2. So we don't have any problems on this interval. Like 0 would be a problem, but 0 is not in this interval. So we're good to go. So the first thing we need to do is get the derivative. I think it's fun that we're using derivatives and integrals all in the same problem. So we bring down the 3x squared over 6. This guy we could write as 1/2 x to the negative 1. So we'd bring down the negative 1. So we'd have negative 1/2 x to the negative 2. All right. And we want this squared. I'm going to go ahead and do that squaring out outside of the square root here, and then we'll put whatever we get in the answer like in down to here like that. So f prime of x squared is, so this would also reduce to 1/2. So we'd have x squared over 2 minus 1 over 2x squared, quantity squared. So first we'd get x to the 4th over 4. Let's see, then we'd multiply these two together, and we'd have, actually we have 2 of those, so 2 times x squared over 2 times 1 over 2x squared. I just put the minus sign out there. Plus this guy squared, so we'll have 1 over 4x squared like that. Let's see, those 2's will cancel, these x squareds will cancel, and we're just left with a minus 1/2 in here. So our derivative squared is x to the 4th over 4 minus 1/2 plus, yeah, I guess they're both on the bottom. Yeah, 1/2. All right. Sorry, I was checking on something there. 4x squared like that. So now our arc length will be the integral from, again, these endpoints. So from 1/2 to 2 of the square root of 1 plus this guy. So this is x to the 4th over 4 minus 1/2 plus 1 over 4 x to the 4th dx. All right, now there is some cool little simplifying that goes on here. You can just go to your calculator and plug it in from here. And honestly, if this is a calculator section, I would definitely recommend just going right to the calculator and plugging it in. But there is something neat that happens with the 1 and the negative 1/2. So those are going to cancel out and change this to a plus 1/2. And now this guy in here becomes, well, exactly what you would get if we squared this with a plus sign instead of a minus sign. So we end up getting that this is the integral from 1/2 to 2 of the square root of x squared over 2 plus 1 over 2 x squared squared dx. And the square root and the x squared, or the squared here, are going to cancel each other out. If we factored this, this is what we would get. All right, it's just kind of a neat little thing that happens. All right, but again, probably just want to use your calculator, so let's practice using the calculator. Like, we could keep going here if we wanted to, but in the interest of time, because I know you guys have other classes and other videos to watch. So let's see, math, number 9. We're going from 1/2, 1 divided by 2, to 2. And let's go ahead and do the square root. I'm going to go do the original back here, just to see what we get there. 1 plus x to the 4th out of the parentheses, or out of the exponent, divided by 4 plus 1/2 plus, actually that was a minus 1/2, wasn't it? Yeah, I switched it when I distributed. Did I? Oh yeah, it was minus. Yeah, back here, minus. Yeah, okay. I was getting lost there. Plus 1 divided by parentheses 4x raised to the 4th out of the exponent. Close the parentheses. We're done with what's inside there. And dx is our variable. And let's see what we get. There it is. So we get 2.0625. And remember, we want at least 3 decimal places. They only gave us 4, so just go ahead and use the whole thing. There's our answer. All right, so that is how the arc length formula works. For the next video, we'll do one with y equals, and we'll do a word problem.